Hello, and welcome to Astronomy 100. In the previous segment, we were talking about the way that we measure light and how we quantify those measurements. And we talked about the concept of wavelength. Now, wavelength is a very, very important concept. Remember, wavelength is the distance between two successive peaks or two successive valleys of a wave. And if you recall, wavelength is measured in units of angstroms, and the angstrom is a unit of distance that's unique to many of the parts of astronomy, but it's a unit of distance that's defined as 1/10 billionth of a meter. And if you recall, we're going to use the abbreviation here, the Greek letter lambda for wavelength. Now, what's really very critical is understanding the connection between wavelength and color. So one of the most important ideas that you could learn is that color is actually light of different wavelengths. So when you perceive colors of a variety of different types, what you're actually perceiving is light of a variety of different wavelengths. So red is one particular wavelength, orange is another particular wavelength, yellow is a different wavelength, green, etc., etc. So color is actually light of different wavelengths. When we measure the wavelength of the light that we see in the form of color, we get a range of wavelengths that stretches from 7,000 angstroms all the way to 4,000 angstroms. 7,000 angstroms is the wavelength of deep into the red, and 4,000 angstroms is the wavelength that's deep into the violet. And so the perception of color is related to the wavelength of the light that you are seeing with your eyes. So let me show you what I mean by this. If you were to imagine light that we'll call violet in this case is coming to your eye perceives the color violet. But it's violet because of the wavelength, the distance between these two peaks here. In this example down here, the light that your eye is perceiving as red is red because it is a different wavelength. So you'll notice that this is a shorter wavelength compared to this. This is a longer wavelength compared to this light. So light of different wavelengths is perceived as different colors. Now, some students have a hard time understanding the concept of an angstrom because it's a unit of distance that is perhaps something you haven't ever heard before or used before. So let me show you what I mean by that. If we were to stretch a ruler, an imaginary ruler, from the peak to this peak, or from the peak of this wave to this peak of this wave, imagine that this ruler is divided into little tiny increments. And if we had a magnifying glass, we'd have the ability to actually see those individual increments. So the distance between these two lines is 1 angstrom. And if I have 4,000 of these gaps stretching all the way across, that would be a distance of 4,000 angstroms. Similarly down here, if this is the ruler stretching from one peak to the next peak, and again a magnifying glass, you can see that each of these is also the same size. So 1 angstrom is 1 angstrom. The difference is you would have 7,000 of them all the way across as opposed to 4,000. So the unit of distance is the angstrom. What we're measuring is wavelength, and light of different wavelengths is light of different colors. So it's a very, very important idea that you understand that color is light of simply different wavelengths and how we perceive that light. Now, what is also rather interesting about this is that because we can perceive a wide range of colors, what that means is that we're perceiving a wide range of wavelengths. And so in this particular image I want to show you here, what we have are just a few examples. You can see that we're going to go deep into the violet, and then we're going to go all the way through the colors of the rainbow or the visible spectrum until we get deep into the red, and some names to go with them as well. But what I want you to notice is that it is all light in the form of a wave, but what is simply the difference here is that the wavelength is increasing as we go from the top to the bottom. So this shade that you perceive as this color has a distance of 4,000 angstroms from peak to peak, or its wavelength, and then light that you perceive that's very deep into the red is perceived as this color, but again you have a distance of about 7,000 angstroms going all the way from peak to peak. What is sometimes surprising for people to know is that color is actually something that is not a reality in nature. Let me show you what I mean. Color is something that your brain is doing in response to the light that enters your eye. I know you think you see color in the world around you, and of course we do every day. We don't think much about it. But the color that you are actually seeing is something that your brain is doing in response to the light that is coming into your eyes. And the way that I'll demonstrate this for you is that there are colors that we obviously perceive as humans, but there are animals on the earth that can't see color like we do. And the example that I'll show you is that this hat that you see here is just a very, very strange, bright color of orange. And this shade of orange, of course, is something that we would perceive quite readily. In fact, you would see this at a great distance, and you would see this, maybe somebody wearing this in a crowd. But this is actually a hat that is meant for deer hunting. And the idea is that the deer cannot perceive color. Deer are color blind. So what a deer sees is a shade of gray that we see as the shade of orange. So the color is the light coming from the reflection off of the material, and when it enters your eye, your brain is attaching the color to it, whereas the deer doesn't have the ability to do the same thing. So what the deer will see when the light enters its eye is a shade of gray. And the purpose of a hat like this is so that human hunters can see other human hunters and obviously lessen the risk of people being accidentally shot when they're deer hunting. So this is meant for humans to see other humans because we can perceive this color, whereas the deer cannot. So color is not something that is actually coming from the hat. It's light of a particular wavelength that your brain is interpreting as the color that you see here. The reason why that's important to know is because in astronomy, we are often looking at objects of different colors, and then the color becomes something very meaningful. And so when we see the color of a particular object in our universe, that color is now related to a wavelength, and that wavelength is now a piece of information about the object that is producing the color. So color is something that happens in your brain. We've evolved to have the ability to differentiate different wavelengths by having it represented as different colors, and it's our ability to attach something visual, or at least something cognitive, to the wavelengths of light that are entering our eyes. So it's kind of an interesting idea that, of course, is related to astronomy as well. Now, the next thing that you can measure about a wave, in addition to the speed of the wave or the wavelength of the wave, is what we call the frequency of the wave. So let me remind you of a couple of things. Remember that we've already seen that a wave travels from one place to another. It travels at a particular speed, and there's a distance between the successive peaks or valleys, and that's called the wavelength. What I'm going to do now is I'm going to animate the wave. And so you can see in this animation the wave is going from right to left. And I want you to keep your eye on this green dot that seems to be going up and down and up and down. The important thing to notice is that the green dot is not going left or right. It is simply rising and falling as the peaks and the valleys go by. If we were to time how frequently the peaks and valleys are going by watching the green dot go up and down, we are measuring what is called frequency. So the definition of frequency is the number of cycles per second that pass a given point, and I'll explain more about that in just a minute. The symbol that we use to abbreviate the concept of frequency is the Greek letter nu. It looks like a V with a little wing on it, but it's pronounced nu, and it's spelled N-U. So the Greek letter nu is the symbol for frequency. Frequency is the number of cycles per second that pass a given point. So here's the idea. What is a cycle? Well, one cycle is when something does something repetitive. Cycle means repeat. So you'll notice that this green dot goes from the top to the bottom, back to the top to the bottom, back to the top to the bottom. And every time the green dot goes from top to bottom, back to the top, that is one cycle. So this is essentially one cycle, another cycle, another cycle. Okay, so one cycle is the green dot going from top to bottom, back to top. If you have a certain number of cycles per second, essentially what you're measuring is a certain number of peaks and valleys that are passing by a given point. The way that we quantify frequency is we use the unit called the hertz. And the unit of the hertz is named after a scientist who lived about a century ago. His name was Heinrich Hertz. It's abbreviated with the capital H, lowercase z. And the definition of 1 hertz is 1 cycle in 1 second. So 1 cycle per second is 1 hertz. So let me give you a few examples. If this green dot were to rise and fall 10 times in 1 second, the frequency of the wave is 10 hertz. If the green dot were to rise and fall 1,000 times in 1 second, the frequency of the wave is 1,000 hertz, or we might say 1 kilohertz. If it rises and falls 1,000,000 times in 1 second, then we would say that the frequency is 1,000,000 hertz, or maybe we might say 1 megahertz. So something that is repeating over and over again is something that is a cycle, and in this case it's the repetition of the peaks and valleys passing a given point. So we have the wavelength of the wave, we have the frequency of the wave, and of course we have the speed of the wave. Now there are other things we can measure about waves, but in the case of astronomy, what we're going to really focus on are just really these 3 measurable things. What I want to do next is show you how the speed of the wave, the wavelength of the wave, and the frequency of the wave are related to each other, because this is a critical tie together of all 3 of these physical concepts. Let me show you what I mean by this. If we were to show 2 different waves, in this case with 2 different wavelengths and 2 different frequencies. Let's start with the top one. You'll notice this wave traveling from right to left, and you'll notice that the green dot is rising and falling, and you'll notice the distance between the peaks there. And the one on the bottom, same thing, another wave right to left, but notice the distance between the peaks is larger. So the bottom wave has a larger wavelength, the top wave has a smaller wavelength or shorter wavelength. But if you remember from a previous segment, all light has to travel at the same speed. So this wave is traveling at the same speed that this wave is. It may not look like it, but they're traveling at the same speed. Now here's what I want you to notice. When the wave is forced to travel at the same speed, what you'll notice is the shorter wavelength makes the green dot rise and fall more frequently. The longer wavelength makes the green dot rise and fall less frequently. So you'll notice that the wavelength and the frequency are inversely related. Inverse means when one gets big, the other gets small. So in this case, if we make the wavelength larger, it makes the frequency smaller, and when we make the wavelength smaller, it makes the frequency larger. So how do we kind of show this in a quantitative fashion? Let me show you how this works. The formula that we're going to use is this one here. The symbol c is the symbol for the speed of light, lambda is the symbol for wavelength, and nu is the symbol for frequency. And if we are forced to keep this value of c always the same value, when we do some algebra to rearrange this formula, for instance, let's solve for lambda, and then again, let's solve for nu, what you're going to get are these 2 formulas here. So notice the frequency of the wave is the speed divided by the wavelength, or rearranging this a different way, the wavelength of the wave is equal to the speed divided by the frequency. Notice how these are inverse. When the bottom changes one way, this changes a different way. If this becomes smaller, this becomes larger, and if this becomes larger, this becomes smaller. So you'll notice down here that the wavelength and the frequency have to be inverse, which is what we saw on the previous slide. What this all boils down to is you'll notice that if we have light of different colors, which is light of different wavelengths, which is also light of different frequencies, you'll notice that when the light is red light, the wavelength is longer, and when the light is violet, the wavelength is shorter. But this longer wavelength, even though the wavelength is bigger, has a smaller frequency, and this wavelength is smaller, it has a higher frequency. So bigger wavelength means a smaller or lower frequency, so they're inverse to each other. Now we're just about out of time, but in the next segment what we're going to talk about is other things that we can learn about the nature of light and what it can tell us about the objects that we're hoping to study. I hope you'll join me.